Hello everyone, my name is Camila and today I'm going to present our paper entitled Last Mile Delivery Considering Time-Dependent Locations. And this is a joint work with Professor Nascimento. So last mile delivery refers to the delivery of items from a transportation hub to their final destinations. And this transportation hub is usually a warehouse where items are stored. And last mile delivery has many practically relevant scenarios, such as in commerce, urban logistics, and food delivery. And in the traditional last mile delivery problem, each item is to be delivered to a single fixed destination. The problem that we propose is called last mile flexible delivery. And here we assume that items can be delivered to multiple alternative locations depending on the time of the day. For instance, the items in delivery D1 could be delivered to the user's home in the early morning or in the evening. And another alternative is to deliver those items to the user's office during his or her working hours. And we also assume that all items are stored in a warehouse W, and our goal is to find a route for a courier such that the number of completed deliveries is maximized. And of course, there are many possible routes that the courier could take. And here I'm going to show you some examples. And we assume that the courier leaves the warehouse at 4 p.m. and must be back by 6:40 p.m. And we also assume that each delivery takes 5 minutes to be completed. So let's say we have this route here, W, L8, L2, L6. And as we can see, the arrival time at L6 is at 6:40 p.m. However, the courier must be back to the warehouse by that time. Therefore, this route is not feasible. On the other hand, this route W, L7, L2, L6 is both feasible and maximizes the number of deliveries that can be completed within the courier's working hours. So as you can see here, all 3 deliveries can be completed. So that is the route that we are looking for. And the work most related to hours is this version of the last mile delivery problem that is proposed in this paper from VLDB. And their goal is to minimize the maximum travel time of the couriers and minimize the total latency of the requests at the same time. However, they assume that each item has a single fixed destination. And the classic vehicle routing and orienteering problem with time windows are also related to our work. However, they do not consider any notion of alternative destinations. And we first propose an optional approach to solve our problem. And this approach is actually an extension of the branch and bound approach proposed in this paper, also from SIG Spatial. And the idea here is to build a tree that represents potential paths that the courier could follow. And this tree is expanded and pruned based on upper bound values. And each upper bound values represents an optimistic estimate to the maximum number of deliveries that can be completed by following that particular branch. And as you can see here, the longest path produced in these 3 is L7, L2, L6, and that is the path that is returned. The optimal approach, however, doesn't scale to large instances because the problem isn't hard. So we also propose an insertion heuristic where at each step, our goal is to find the best location to be inserted into the courier's current path. More specifically, we look for the location L and position I in the courier's current path, such that the difference between the travel cost of the path that is obtained after insertion and the travel cost of the courier's current path is minimized. So this figure here illustrates the insertion of location L at position I in the courier's current path. And the naive insertion is to consider all candidate locations and all possible positions in the careers path. However, this can be very inefficient. So we actually propose an insertion heuristic where we compute lower bounds that we use for pruning unpromising locations and positions. And this lower bound is an estimate to the actual time increase for a location L and position I. So here I'm going to show you some examples of how we compute those lower bounds. So let's say we have the route W, L3, W, and that we want to insert L5 at position 1. So L5 will come before L3. So we first estimate the travel times from W to L5 and from L5 to L3 by using their Euclidean distances. And as we can see, the arrival time at L3 is at 1:70 p.m. However, there is no valid time window for L3 at that time or at a later time. Therefore, this path is not feasible and the lower bound is actually infinite. However, L5 can be inserted after L3, and in that case, we get a lower bound of 39 minutes. But this lower bound is not necessarily greater than 0. For instance, let's say you have this route here, W, L6, W. And as you can see, even though the courier arrives at L6 at 5:10 p.m., the departure time is only at 5:45 p.m. because the courier has to wait for a valid time window. But that waiting time can be potentially used to complete other deliveries. So, for example, if we insert L2 before L6, even though the arrival time at L6 is a little later, the departure time is actually the same. And therefore, the arrival time at the warehouse will be the same. And the lower bound is actually 0 in that case. And we also prune paths based on an estimated latest arrival time at each location. So here in this example, we assume that the courier leaves the warehouse at noon and must be back by 2:30 p.m. So the latest arrival time at W is 2:30, and at L7 is 1:55, and at L3 is 12:55. And this means that, for instance, if we build a path where the arrival time at L3 is later than 12:55, then that path can be pruned. So here I'm going to show you an example of how we actually select the best location to be inserted into the careers path for a given iteration. And we are show this example is for iteration 1. So we first build this a list of lower bounds, and for each element we have a location, its lower bound, and the set of positions where that location can be inserted into the careers path. And this set is computed when we compute the lower bound. So we first consider L7, and then we compute the actual time increase for L7, which is 65 minutes. And then we consider L2, and the time increase is also 65 minutes, but for L8, it is 85 minutes. So the minimum time increase is actually now smaller than the next lower bound. So we have already found the best location for that iteration. And then we insert L7 into the careers path. And in our experimental evaluation, we have used the GeoLife dataset of real trajectories in Beijing. And for each user, we selected the trajectory with the largest number of stops, and we considered that stops of at least 30 minutes are potential delivery locations. And by doing so, we obtained 160 trajectories. And here we have more details about those trajectories for each stop duration. And the number of delivery slots represents the number of different time windows, and the number of stops represents the number of different locations to be visited. So, and in this first set of experiments, we compared our insertion heuristic and the naive insertion heuristic to the optimal approach. And as we can see here, the processing time increases with the carrier available time and also with the number of deliveries, but the optimal approach is much more affected by those parameters. And in fact, for 20 deliveries, it couldn't find a solution in less than 1,000 seconds. And these bottom charts here show that the results produced by both heuristics are actually very similar to the ones produced by the optimal approach. And in this other set of experiments, we considered all 160 deliveries. And as we can see, our proposed insertion heuristic is much more efficient than the naive one. And also, they produce the same results as expected. So to conclude, we have proposed the last mile flexible delivery problem, where our goal is to maximize the number of deliveries completed by a courier. And we also assume that each item can be delivered to multiple alternative locations depending on the time of the day. And we first presented an optimal approach, and then we presented an insertion heuristic. And our experiment showed that our insertion heuristic is orders of magnitude faster than the optimal approach, while still producing very good results. And as a future work, we'd like to extend the last mile flexible delivery problem to consider multiple couriers instead of just one. Thank you for your time.